Okay, folks. So thank you very much for your patience here. Unfortunately, I'm still very ill with what's been diagnosed now as influenza. So I'm having my handy mask if I start engaging in bouts of coughing. And I apologize if today's lecture is less energetic than the normal ones. I was in bed all day yesterday. I think I hit the bottom of my trajectory, and we'll try to get through this lecture and communicate some of this material. For anyone who wants to meet with me, I apologize because the discombobulated schedule. I know it's been a bit harder to meet with me, and I could do so between classes. So I teach 371 in the afternoon at 1. And between those, I have a bit of time. If you absolutely cannot make it there and you need to speak with me, after 371, which gets out at 2:30, I could probably do it. But otherwise, I'm going to go back to bed. The doctor said just get as much rest in, and I've been trying to do that. And we'll have to see how it plays out over the next few days for future plans. Anyway, thank you for your accommodation. Today's lecture is going to be a little bit different. Josh, if we could get the lights back there on the left-hand side. Like so much of the material here at 470, it's new stuff for me to present the first time. And I welcome feedback on it. This lecture is a little bit more advanced. And for those who are graduate students in the audience, it may speak to you more. But what I'm going to try to do is to undertake a challenge, which is there's a very important feature of Java's libraries, which are what are called monadic types. And these types give us some real advantages. And they're a very important set of the functionality that Java 8 offers. But to understand that it can be challenging because there's some concepts involved that are pretty rich and hard to present in one lecture. I'll try to grapple with this and do my best. Rest assured that while the material here is going to be conceptually deep, you're not going to be responsible for all nuances of it. But for those who are interested in this, it may help you appreciate some of the features that maybe you struggled with in your problem set too. Okay, so I'm going to try to introduce this notion of a monad, which is kind of sweeping a bunch of different languages now. It has its home in functional languages, but you'll see it manifested in many other languages now that have mixed models of computation. Java 8 is one of them, but Scala would be another one. Clojure, of course, another one is one that's explicitly functionally oriented. But even in Python, you can build monads, and it's a useful notion. So, ladies and gentlemen, as you saw last time, and as we saw some in Python, the notion of performing sequences of computations as pipelines of sorts, where we operate on this, we pass it to that, and it processes it like this. Maybe we go get some data from the database and we filter it by this, and then we map it in this way, and we go and reduce it in this way and summarize it in various fashions. It's a very powerful way of describing a computation that's pretty clear, it's transparent, it's quite concise, and it's very modifiable. You can insert a new filter in there very easily and in a modular fashion. So it's got a lot to recommend it in terms of representing it compared to whole sequences of loops and if statements and stuff like that. It's very compact. Okay, and an example is here where last time we used Java's collectors in order to count, say, the number of people who are infective according to age categories. So we could take this population stream. Oh man, sorry. Okay, I think the cable's as sick as I am. Hopefully I'm a bit more predictable than it. So I'll frog the cable. I apologize. I know that's almost unreadable. So we have this ability to take a population, which is initially defined, say, in an array list, or what have you, and to turn it into a stream, where we then filter it by certain characteristics. So we select out people who have matched a certain criteria, to wit, they're infective, and then we collect them in a way that sort of partitions them into age categories, and for each age category we count up the number that are applied there. So a very compact way of expressing what otherwise could take, a page of code or something like that, particularly the partitioning and counting up in each partition and that sort of stuff. Maybe more to the point, it could be easily modified to filter by an additional criteria, or to divide it up according to other sort of categories of division. Okay, this is a most unfavorable cable. Okay, not a good thing. Okay, oh man. Okay. This is okay. Oh, I thought I had the trick, but I'm off. Okay. Badness. Okay. Well, I can just hold it. How's that? Okay. We'll hold it for now. Okay. Okay. Now, this is a very nice concept, to be able to have computations phrased in this fashion, phrased in this pipette filter fashion. But it runs into some challenges. For example, where we have a nonlinear flow of control. Fancy words. What do I mean by that is, well, imagine most of the time this works well, but maybe there's some times where there's null values, right? Where, for example, a person's age isn't recorded, and therefore, this computation doesn't quite work. And often when we have computations going on, we deal, with a standard case, and then there are these exceptional cases. An exception is thrown, or a null value is present. And in traditional computation, how do we handle that? Well, we put in if statements. We put in try-catch blocks. We go and we handle things in that way. And if we have asynchronous computation going on, maybe we do this computation, but we do it across multiple machines because we're dealing with 30 million sort of individuals here. So we want to map it over to different computational units. To do that in a traditional way requires doing things like writing callbacks and so on, or often does. And those sort of asynchronous computations, a situation where not everything is going in lockstep, but things finish at different times on different machines. Often handling that requires a lot of scattered code in many different places. So when a machine's done, it calls back and says, hey, I'm done. Okay, so it's a nice idea to be able to perform things in this way. It's a beautiful concept, but it is stymied. The fly in the ointment is with some uncomfortable facts, that sometimes we have irregular conditions occurring. Okay? And we get messy code because of it. I don't know how many of you have ever been in a situation where you'll have a structure, and in the structure, so maybe you have one class and it refers to an instance of another class, and that refers to an instance of a third class, and you want to get some item out of that inner class, that third class, that innermost class, nested, through several others. But any of them can be null along the way, so you have to put in null checks, Is the first reference to the first one null? If so, return null. Is the reference to the second one inside the first one null? If so, return null. Is the reference to the third one inside the second one null? If so, return null. So you have this series of if statements, nested if statements. If it's null, if this is null, if that's null, and it gets messy. More to the point, it gets in the way of understanding what's going on. One of the nice features of this, and I recognize this is new to a lot of you, but you can learn to read these in a very intuitive way. We start with this group, we filter it by this, maybe we map it by this, and then we collect it by this. You can learn to kind of read it in a very sensible fashion. Whereas if you're dealing with exceptions and there's all these things for if it's null and to handle an exception, etc., it can kind of get in the way of understanding what's going on. So these monads we're going to be talking about at a high level, they can play a very important role in addressing this problem. They can turn what is going to be a scattered computation normally using traditional try-catch blocks, using traditional if statements to handle nulls, into a nice, beautiful computation just like this one. So we can still do this even in the presence of those exceptional conditions. So we can still handle cases where this stream is empty, for example, or cases where we have a null person or what have you, okay, where we have an empty person. So what is this monad? What's a monad? Well, a monad is a kind of type, okay, and it has special structure to it. Structure not only in terms of the information it maintains, but in terms of the operations it has, okay, and this allows software developers to kind of create. It's what's sometimes called programmable semicolons. So if you have a sequence of operations, kind of like this one here, to give one example, if you need to perform a bunch of things in a row, you can define what information you want to carry along with the actual values, what other information you want to carry along to accomplish the job. Okay, so when I say programmable semicolons, I mean the semicolons, they allow you to carry more information around, do custom things, maybe log. Every time you compute a value, you log it out to some log file or something like that. Or maybe you keep track of where values originated in the program for auditing reasons. Or maybe you keep track of whether the value is empty or whether you indeed have a value there. So if it's needed later and it's empty, you'll just return an empty thing for the next step. So in short, it allows you to kind of take what's normally done in the normal processing case and add some information to it so it can be more, it can be handle a much greater set of cases, including these exceptional conditions, special cases, etc. Okay, so it turns out that if we use monads, these things called monads, we can handle all of these cases in this sort of way, in this way of having a nice, clear, pipelined computation, pipe and filter, okay, just like back in the Linux shell, okay. Here we can really simplify the computations. We could take something where the code would be scattered all around and have to deal with these asynchronous callbacks and if statements for nulls, and we can put it in a nice context where it's just expressed like this, and all that stuff is done just in a clean sequential way. Okay, so that's the sort of goal of monads. Now, how does it do it? How do you actually keep this information in the necessary way? Well, ladies and gentlemen, this is where it gets a little bit more textured. So basically, I like to think of a monad as kind of being a package around a value. And you'll find other people commenting on it. They talk about bubbles around values or boxes around values. I tend to prefer to think about it as a package because the package, well, all we know, I mean, we buy things these days, and often just getting the thing open is a major job. The package is got a lot of things there in it. It's very hard and has a lot of a lot of things we have to get through. The point is the package is going to accumulate information. The package is going to do things. The package itself is quite often significant beyond the value. So it's not just a bubble that's almost empty. It's this package we're going to put around these values is going to be responsible for certain types of doing certain types of things, like logging messages. It's also going to be responsible for keeping track. For example, is a given value computed yet? Or is it yet uncomputed? In which case, if we need it, we need to compute it. It's going to keep track of whether a value is empty or whether indeed it has something there already. It might keep track of where this value originated. Where in the program was this value first computed? Like, where was it calculated? Where did it come from? Which user calculated it, or which user was used to access the database for this value. So we're going to have these packages around values, and instead of just operating on values that are computed, adding them together, dividing them, storing them, we're going to actually keep track of this package information additionally, okay, around these values. And if you think about what we talked about before, when we talked about Java's features, streams, optionals, and we're going to talk about completable futures more, but I think we hit on them last time. Each of these kind of fits this value. So with a stream, the package around it is going to keep track of like where you are in the stream, and keep track of the next value to get to. Optional is going to keep track, is this value actually, is there a value in there, or is this thing empty? If we have an optional, it could be that it's missing. It's a missing value. And that's what an optional can represent. You have an optional value here. It's not sure that you have a value, because it might be you gave the stream to a reduce operation with an empty stream, in which case you don't get out a meaningful value. You get out an optional that's empty. It's not a real value. Okay, it's an empty value. Completable future, that's going to be like this guy here. Once it's computed, we'll keep track of that value. Before it's computed, we need to know, okay, it hasn't been computed yet, so if it's needed, we'll compute it. Okay, so all these are examples of monads in Java 8. They keep track of some values to be sure, but then they keep track of this metadata, the data about those values, and maybe other metadata too, like this, like where it came from whence it came. Okay, so it turns out these are well supported in the Java libraries, and indeed in Java 8, these are some of the most exciting things there. And even in my convalescence, I get excited about them. But it turns out there's third-party practitioners for Java libraries that are providing lots of additional types like this that are these monads. They provide extra good uses along the same lines. They make it very convenient to do certain things. Okay, so why do we use these monads? What's the use of them? Well, one thing is to maintain metadata concerning the value. Okay, so we like to keep track of information about this value. Okay, one of the most useful types of things is to keep track of exception of values. Is it empty? Is it null? Is it or NA? And by keeping track of the monad, we can handle it in a pipe and filter fashion. Okay, so sorry, this is I've lapsed in my control over this. My hand is getting quite painful. Okay, there we go. Okay, and we can maintain contextual information, like where this came from. Is it computed yet? And as I said, programmable semicolons, the idea is we can do extra things during this. And the example I gave was logging or tracing what's going on. While you're executing the code, you're doing all the normal things, but you're reporting this extra information. And 371, recently I gave an injunction. Perhaps I gave an exhortation to compute, to perform logging. scalable fashion, in the sense that you can scale it back, or throttleable fashion. You can throttle it back or do more logging without changing the program, just by changing a config file. That's an example of kind of this programmable semicolon idea. But we don't have to scatter that in our code. We can just turn on the monad that does logging, and we're off to the races. Okay, so they allow us to handle in this sort of fashion, because this is just a value. A monad is, ladies and gentlemen, just a value we're passing around. One thing returns it, and the next thing takes it up, maybe adds it to a different one, and gets back a value. All that additions and all those operations on it, the storage of it, etc., that's being performed not only the value that it contains, but also in the whole monad. So it's like a value that wraps up this extra package information. And by doing that, by having these values that record, like, I am some exceptional condition, this error has occurred, or I'm empty, we can use the basic values in this fashion. We don't have to put in a try-catch block. We can just have it keep track of the fact that I'm exceptional right now, and that can be at the end. If it's an exceptional condition, we'll handle it a different way. The point is, then we can still use this. We don't have to deal with the special cases by putting in lots of other mechanism. We can just handle the special cases in a standard way with these pipe and filter computations. Kind of the idea here, okay? So it allows concise and clean, that is, think pipelined computation, handling of alternative execution flow. These cases that we normally have to put in all these if statements, all these try-catch blocks, all these callbacks. We just do it in this standard sort of way, because we're keeping track of this metadata that gives us the required information. That's kind of the idea. So it provides a clean functional route to capturing these things. Now, next week, the topics covered in this class, if necessary, likely by videos, will be on something called aspect-oriented programming. Okay, and some of you, and that's one exciting avenue for extending languages, including languages like Java. And there's a very popular framework, Aspect-J, that we'll be covering for Java, that's widely used, including in the popular JUnit testing framework. But some of you may have experienced inversion of control mechanisms, or what I call dependency injection. If you've ever used Java Swing, for example, certain Apache libraries, they make use of what's called inversion of control. And it's a very popular mechanism, ladies and gentlemen, for performing computations in a richer context. If anyone's used, well, you all used for problem set 2, you would have seen any logic uses inversion of control mechanism. The idea is we keep track of this contextual information that's told to values. And it turns out monads provide us a way of realizing aspect-like functionality, inversion of control. Okay, so what are these monads? We have lots of cases of them: stream, optional, completable, future. What are the defining characteristics of these things? Well, I said it's a type, right? What is a monad? It's a type construct. It's sort of type, okay? It includes values of, if we have a monad of type A, it includes a value of type A. It keeps that value around, but it keeps metadata on that value too, extra information. And it not only keeps that information, it provides extra operations. So it's kind of defined by 2 functions that it supports, okay? One of these functions, it goes by various names. Confusingly, this function, get this, folks, this function is sometimes called return. I know that's going to be, it's hard to talk about it, right? It's also called unit. It's also called pure, neither of which, to me, are very nice to use to talk about this. But basically, this thing takes a value. It takes one of these guys in here, and it creates a monad around it. It creates this package. It packages it. So it takes a value and it puts it in a package of the appropriate type. Okay? So here we have foo as a string, and we are going to call this function pure unit return, whatever you want to call it. It gives us back a package around this thing. Okay? It's going to be a package of a certain sort, the monad package. So it's going to be one of these guys. It's going to be, this one that keeps track whether or not it's empty, or this one that keeps track where it was computed, or this one that keeps track whether it's computed yet. It's going to be, it creates a monad from it. Okay? I'm writing this to indicate a function from A to the monad. Okay? So we talk about it injecting the value foo into this package, but we package it basically. Okay? And an example of this that we saw last time, is this one here, where we had an optional of integer. So this is something that might contain an integer, but it might not. And we say this optional dot of a, and a is an actual integer. And so this will create a monad that contains this value a. Okay? Why might you want an optional? Well, imagine you're writing square root, right? It returns an optional of double, for example. Assuming you're not dealing with complex numbers, if you take a square root of a negative number, maybe it returns an empty value, otherwise it returns a double. So this is an optional, say, of double of the number that's returned, otherwise it could be empty. And there's a way to create an empty value in optional as well. I think it's dot empty. Okay, so this is one of the methods supported, okay? One of the functions, as it were, supported, the functionality supported by a monad. It's this thing. Create a monad out of a value. If you have a value, create a monad around it. We package it. Are we okay with that? Okay. Now, the next one is more complicated. Okay. Next one is more complicated. And that's this thing called bind. Okay. And bind's functionality, signature is given here. Can anyone read that for me? What, in broad terms, what does it take as arguments? Should learn how to read these things, preferably before a final exam. So what does it take as arguments?
Two predicates.
Okay, so this is indeed a function. It's a function from A. So we have a monad of type A, and this is a function of from A, not from monad of A, but from A to a monad of B, of another potential type. Could be A, same as A. So maybe we have an optional of int, and we do a square root on it. We get out an optional double. For example, this would be something that maybe it's a square root operator, and it takes in an int, and it returns an optional of double. Does that make sense? So this would be some function. That's its second argument. This x, it's actually not an x, although you can't tell it. Even if I gave binoculars, you couldn't tell. The only way you can tell is because it doesn't have extra typographic stuff. This basically means a pair of these things. So this is the first argument, this is the second argument. Okay, that's how we write sort of successive things here. And this is what it returns here. So the first thing it takes, the second thing it takes, as Mahmoud said, is a function. Okay, what is this thing that it takes, this first thing? It's a monad of type A, okay? Monad of an int. That's the value it has now. This is the value it's going to apply to that. And out it gets a what?
Monad of a different type.
Monad of a different type. It gets out from applying this value, this function to this monad, it gets out a monad. It gets out an optional double, say. We passed in an optional of int, a function from int to optional of double, and we get back from applying this guy to this guy, we get back a monad of double. In other words, an optional of double. Okay. This is bind. Bind is given two things to do its job: a monad and a function from the type inside of that monad to another monad, and we get out that final type of monad, okay? And what's the job of this in life? Well, its job is to compose functions. It basically performs the next operation. This is kind of the next operation to be performed. This is the value that it has going into that operation. This is what it gets out. Yeah.
Would the monad of type B have to maintain the metadata or
Exactly.
around M?
Exactly. This monad of type B is, in fact, it's often accumulating metadata, like keeping track of how was this function derived. Like maybe based on M of B here, maybe it's M of B here is going to keep track of what was done here and keep track of what was already in A. So it's accumulating a full history of where this value was computed over time. And that's what this monad is going to do. We provide, as creating the monad, we provide our own custom bind. So just like was asked about here, we can actually accumulate whatever information, this metadata in M of B, this monad of B. We can accumulate the metadata from A and add to it whatever information we want to about how this was computed, and get out this extra data which includes the metadata and the actual value coming out of it. So this bind allows us to take the next step, okay, the next step in the computation. And really it allows us to kind of compose these functions one after the other. We can apply these functions, and we're accumulating whatever information, the metadata in M of B, right? Just like Eric emphasized. It's exactly right. So let's talk about it. So this is the second argument, is a function that takes an A, and this is important. It takes an A and returns an M of A. So again, it might be the square root operator, right? We're applying the square root function. It takes in maybe it takes in an N, just to make A and B different, and it returns an optional of double. What it doesn't take in, what this function doesn't take in is a monad. It takes in just the value and it returns back one of these. This monad that returns often accumulates some information from this guy here, but also from this guy. Okay, and this M of B is the thing that will be given to the next application of bind. We're going to give it whatever we got out last time. We'll give it here, and we'll have another operation applied to it. And we'll get out another one, and we'll take that and apply another operation to it and get out another one. Are we okay with that idea? Yeah.
For the function in the pair, can it be basically just a producer that it's always providing this type always, no matter what the first pair is?
Yes, absolutely, absolutely. Yeah. So ladies and gentlemen, it's not necessary that, for example, B be different than A here. This function might always return a double or something. It's not like we have to provide, I've written this in a general way, but we don't always have to parameterize this in some fancy way. What I wanted to emphasize by listing A and B is we might take in a value that has one type inside, and maybe we apply a two-string operator, and we get a different one, a different type of monad, a monad that has a different type of value. We took in a double, and we get something out, a monad with a double in it, and we got something out, it's a monad with a string in it. That's okay, but generally, our functions will have a very particular type of B associated with them. Okay, so let's talk about some examples. I know that's kind of abstract. So a monad is this box, or this package that keeps track of this information, and it's kind of defined by these two functions. And these functions operate on values here and return back a monad here, and they inject this value into a monad. But it's going to keep track of other information, this metadata around it. So let's consider stream, okay? Let's consider stream of X. Stream of X, ladies and gentlemen. A good thing. That's what we were using back here, right? Streams. We took the stream, we filtered it, we collected it. We could have had a reduce in the way, or a map in the way, where we mapped each person to their double age or what have you. Okay, so let's consider stream. Okay, here, ladies and gentlemen, we specify functions on the underlying value when they're when they're present. And you know, if stream is empty, we'll just have them return an optional that's empty. Okay, so let's consider you know, if you're reducing them, for example, computing a value. Okay, so here's these two operations. Here's this unit thing, which lacks a good name as far as I'm concerned. So here you could say stream of these things. Do you remember that? We could create a stream of known values. So value 1, value 2, value 3. This isn't the only way. We can produce streams in many other ways. But this is one way that we turn actual values into a stream, into the monad. Stream is the monad. And we take a value and we inject it into this stream, okay? That's exactly, hey, come on. Sorry, I'm one-handed here and I am exhibiting dysfunction. So here we have a value, we turn it into a monad, that's what's going on here. We have a value and we create a stream out of it, okay? That stream contains the value, contains those values, but it contains other metadata also as well about them, okay? Here's bind, ladies and gentlemen. Here's bind. This is using a thing that I mentioned last time, but it's actually called flat map. Now, for flat map, I'm going to need to show you something, okay, on the board here. So I'm going to need to relax this, and all sorts of dysfunction will take place. Fortunately, internet users will be in complete mystery about why I'm throbbing this cable and so on, because they're seeing a perfectly clear screen. Okay, so I want to talk about flat map. Ladies and gentlemen. Boy, is that nice. My hand is real. Okay, ladies and gentlemen. Okay, so here we have a stream, okay? And let's suppose we have a stream S, okay? It's a nice stream, okay? Trust me. And this stream, suppose we were to suppose this is a stream of integers, okay? And suppose we were to perform a map with this stream, which is going to map it into a different stream, right? That's what map's job in life is. Can anyone tell me, how would I write a map if I wanted to take each element of the stream, produce a new stream, where the elements of the new stream are the square of the elements of this? What would I put in here? Suppose I want to use Java 8's anonymous function. Syntax. Well, begin paren, I could say x, and it goes to x times x, okay? There we go, okay? So here I take in a stream of integers, say, and I get out a stream of integers, okay? Okay, we okay with that? So this is for mapping, right? Alternatively, I could take that stream and I could map it with a function that takes in an x by putting its begin paren, x, end paren, arrow, and I could take square root of x. This is a stream that takes in, it's a stream of ints, and it's going to return, or it's going to lead to, the result of this will be a stream of what? Of doubles, yeah. Remember, this stream could be arbitrarily long. It could be unbounded stream, right? It could be, what I'm giving it is the stream of primes, right? And this stream that I'm getting out is the stream of doubles that are square roots of primes. Because streams are lazy, it's not actually going to compute them until I need them, right? Okay, so here we have a stream, and we can have stream take in a value, put out a different value. So ladies and gentlemen, here, the fact is, we may have a stream of ints. So A is int, the type parameter A is int, and we get out a stream of B's, a stream of doubles. So we have different type parameters. We get out a stream of doubles here, but we got a stream of A's, of ints going in. And that's because we gave it a function here, this square root thing that perform the square root, where it's going from an int to an optional double. Okay. Anyway. Okay. So, ladies and gentlemen, this is all fine. But I want to ask you this: what would happen? What would happen, ladies and gentlemen, if we said stream.map, and I'm going to, for lack of good imagination here, do something very simple. We want to map this stream so that each element in the stream, x, we get back a stream, okay, stream of A of the value -1, the value itself, and the value +1, okay? So what's the result of this? What's the stream coming out of this going to contain? So again, I have a stream, S, and I map it where the function for the mapping is doing something. And what is that function? Well, it's taking in a value, an integer, and it's returning a stream. Returning a stream, which consists of, in this case, 3 things. Okay? So what is this stream going to look like that comes out of that?
It'll be a monad of monads of
Yes. Yeah. It's going to have this stream that comes out. Well, it's unbounded potentially, so I shouldn't draw a right boundary here. You know, the stream maybe if the original integers might have had, 1, 3, 7. What am I doing? Man, where's 5 here? Sorry. 1, 3, 5, 11, 13, right? Streams of nice things. Okay? Okay? And when I get out the result of mapping the stream to a stream, what I've got out now is a stream of what? Is it a stream of integers? No, it's a stream of streams, right? So this guy 1, what he turned into is what? 0, 1, 2. This guy 3, she turned into what? 2, 3, 4? Yeah. I think I'm not at my best. I'm actually highly dizzy at the moment. This one goes to 4, 5, 6, right? 5 goes to 4, 5, 6, right? So this is a stream of streams, right? I mean, pardon me for not being able to denote the streams well, but these are streams, right? This is kind of like a box of boxes, a set of packages, right? But that's what we get out of map, because after all, we just said turn each thing in the stream into one of these guys. So what Java provides to deal with this, for both optionals and for streams, is something called, you might find this hard to believe, but I tell you it's true. It's called flat map. Okay? S dot flat map. And I think it's a capital M. Maybe. Yeah. Yeah. Okay. Thank you. Good. Thanks. Okay. Okay. It's called flat map. Okay. And we could. I won't write this again. Maybe you'll thank me for that, given my writing. This should be a stream. Okay. Okay. So here's flat map. And what a flat map will do, instead of having those box of boxes, a package of series of packages, it's going to actually concatenate all these streams. So you get one stream out. One stream, ladies and gentlemen, to rule them all. And that stream would look like, tell me the first bunch of elements of that stream.
0, 1, 2, 2.
Good. 0, 1, 2, 2, 3, 4, and 4, 5, 6. Forgive me for choosing an uninspiring example here. But point is, it takes all these substreams, all these internal packages, and puts them just in the main package. Okay? So that's flat map. And it turns out that that is in fact what the equivalent of bind is for streams. Okay, it's this thing flat map. Okay, now I'm gonna frob this cable some more. Okay, great. So flat map takes in a stream as its first argument. I mean, that's what we apply it to a stream. We say S dot, and S is kind of the first argument of it. Okay, remember in Java 8, you can kind of treat the thing it's applied to as a first argument for Java functions, and then it takes in a thing which maps from ints to stream of ints in this case. So B is the same as A, and out we get a stream of ints. Okay, flat map. Okay, let's go look at optional. Ladies and gentlemen. Okay, with optional, here we're representing a type which might be present or might not be. X, it's either present or it's empty. Okay, and it turns out it's really useful for stream functionality. If we do a reduce, we'll get out an optional of that thing, because if we give it an empty string, it's going to return an optional that's empty. Okay, and it's really useful for representing null or not a number, NA, or empty things. Okay, so what are these methods here? Well, unit, this thing, pure or unit, that's this optional thing here. We talked about it earlier. And bind here is also a thing called flat map. Okay, so what does flat map take in? Well, it takes in, ladies and gentlemen, an A, and it returns an optional of A. Okay, returns back an optional of A. Now, for optional, this notion of mapping might seem to you confusing, but let's talk about what would provide. Suppose you had an optional. There's some very strange acoustic effects going on right now in my head. My ear is somehow half hearing, etc. So I'm hearing strange, odd, sort of sometimes loud, sometimes soft, or what have you. Okay, so ladies and gentlemen, suppose we have an optional. Okay, I need to, in the interest of room equity, I need to have some things over here. Okay. Okay, so suppose we have an optional of an integer. This, after all, is a Java generic, so this needs to be some package thing. It can't be a built-in type. It has to be a reference type. Okay, optional O, and suppose we do O of map. You could say, can map this O. That may seem strange, but if we give it a function for mapping, the optional, that function is going to be from integer or int to something else, something it can turn an integer into. So this could be taken an x, and it could apply, I don't know, x squared. Okay. If we map it with this, what do you think it's going to do? If we give it an integer with 2 in it, what do you think it's going to, what am I doing? Sorry. What is it going to give out? 4. Yeah, good. If we give it a value O of 0, it'll give out an optional containing 0, right? Good things. What if we give it an optional that's empty? Okay. It actually will return empty. I believe that's the case. I'd have to go back and double check it. It actually will return empty. Okay. So that's good. It'll handle that case well. So yes, if you give it an optional that's empty, it gives back an optional that's empty. Okay. Which is really nice, because you can, if you want to square something if it's present and otherwise just return empty, this is your ticket, right? Okay. But ladies and gentlemen, the plot thickens. Okay, what if we wanted to do something like this? Map. Okay. Now I can write the two at once. That's right. Okay. Okay. I haven't seen that iteration before. If only I were ambidextrous like my wife. Then I could, imagine that. I could start in one sentence, end of the sentence, front of the sentence, and meet in the middle. Yeah, so ladies and gentlemen, suppose we want to take the square root of these integers, or in fact doubles, right? Where square root is defined to return, suppose we define it here to return something that's an optional of double. So it might be present, or it might have an empty value. Now we can't apply this with map in a standard way, because if we give it, suppose we do it, well, there's a problem if we apply this. What will happen if we give it an optional that is an optional value that's negative, okay? What if we have an optional of integer that's given oh damn, where's my other one? Optional of integer. Man, this is really interesting. Okay, not very effective.
Asynchronous lecturing is a very new method.
Yeah, right. Optional -1. And suppose we applied it, so we said O dot map, so we have an optional of -1, and we applied this map where it takes the square root. And suppose square root returns an optional. What will we get out? What sort of thing will come out of this? So we have this, call it O2, that's holds them up, I'll call it O -1. -1, okay, -1, and we apply the square root to it. What will we get out? We'll get out an optional that holds a what?
Empty.
Okay, actually the optional is going to hold an optional. That's the problem. Because this guy here, it's just mapping each function. It's just like this case over here, where we turned each element into a stream. We had a stream of streams. Now what we've got coming out, if we just do it with map, we're going to have this optional box, this kind of package, and inside of it will be another package that will happen to be empty. And that's not what we want. We don't want to have packages inside packages and infinite regress. It's packages, ladies, all the way down. We don't want to have that. We want to instead have a single empty, just like Eric was saying. So how do we do that? What do we use instead of map? We use flat map. Okay, so ladies and gentlemen, instead of saying map, O dot map of this thing, we say instead O dot, okay, this is going to be really interesting. Okay, sorry, this is not very effective. O dot flat map, right? Flat map. Okay. Well, okay. You get at least something else out of this lecture. Okay, O dot flat map, and this is a paren here, yes, right. Okay, I'm not even gonna do it. This I need to practice before I inflict that on you. Okay, square root of x. Now, what we're gonna get out, if we do a flat map, we will get out, as Eric said, if we give it a -1, it will return an optional. Okay. Now I'd have to get my toes up there. Optional that will be empty. Okay. This will just be an optional of empty because we flat mapped it. We haven't just mapped it where the element goes to itself an optional, which is inside of our optional. After all, with map, this is a function we're giving it from what to what. Well, here this is a function from value to optional, and that's just being applied for our value. And as a result, we get out an optional inside of an optional. We're applying it to our value inside of the optional. But with flat map, we actually are applying it, ladies and gentlemen, so that we get out a value that is for the entire optional. So this is an optional that's empty, okay? That comes out of it. Just like we flatten those streams over there, turn them into one big stream, we flatten this value. So instead of having a package inside of a package, we just have one package. Does that make sense? Okay. I know it's a hard concept for me. There's a beautiful cartoon, if you look for it online, and you're welcome to do it right now, which shows two people. I think it's a man and a woman, and sort of sitting on a hill, lying down on a hill, watching the clouds above them. And one says, every once in a while, I think I understand monads, but then it passes. Something like that. Monads are hard to get your mind around, but flat map basically provides a way of taking what would be packages inside packages and just creating a package of it. And that's exactly what we typically want with bind. So if we have a value, if we have a, oh, wow. Okay, I've been liberated from my hand job. Okay, so ladies and gentlemen, so if we have bind and it takes in a value and it takes in a function, we return a monadic value. This function here is mapping from value to monad, right? So here it was taking the square root of a value, which could be which is an optional of x, and it gets out a monad that is itself an optional, which is highly desirable to instead of having this sort of packages inside packages. Now, why is that useful? Because it allows us to have things to which we apply it, like this square root operator, which themselves return optional values. So it's not merely that we want to be able to apply map to a value that's empty and the result is either empty or not according to the original value. Instead, now with flat map, ladies and gentlemen, we have a value that might be empty. O might be empty, right? If O is empty here, this is a key point. If O is empty and we apply flat map in this way, we give it a square root operator. What is it? What do we get out? So if O is empty, what do we get out from this? We get out if O were empty, should say O1. Okay, so suppose we have an O, and O is empty. What do we get? We apply flat map with this thing. What do we get out? We always get out
another empty option.
An optional that's empty. Suppose that O holds the value 4. What do we get out of this? An optional that holds what? Again, suppose square root returns an optional double. If we do O is 4 and we applied flat map to it, what do we get? 2. Get 2.0. Suppose, ladies and gentlemen, that O is it's an optional holding -1, and we apply flat map to this one that maps the values to square roots. What do we get out? An empty optional. So in short, ladies and gentlemen, this here will give, the doctor probably would be horrified, this value we get out might be empty if either this was empty or this guy returns something that's empty, right? That's what flat map gives us. It's that ability to kind of take into account something that was already already had this as empty, or which when we applied this thing to it, it was empty, and we get out an empty in either case from that. Okay, so ladies and gentlemen, with optional and with monads in general, this information here, it's just like what Eric was saying before. This result here, in that sense, it accumulates values. Either if this was empty or this returned empty, we get an empty out. So it's accumulating more information. Let's talk about completable futures. So here we're representing a type, something of type X, but it might not yet be present. It might not have been computed yet. Not yet have been computed, okay? And this type is key for sort of supporting asynchronous operations in Java 8. And handling this in a really principled first-order way allows for really clean code. We can express a whole series of operations very, very cleanly, leading to a computable future. So the idea here is that we will specify functions to be executed when ready, when the value for them is ready. Okay, and we have equivalents for units for unit, where we basically take your value and inject it into a monad, and for bind with then compose a sync. Okay, so we're going to take a look at that now in just a minute. To give you a sense of something totally different, something like logging, here unit, this guy here, will just package up the value. Nothing extra information gets added on, but bind will print the information out. Maybe save it to a file. Maybe it will accumulate it in the console, whatever. But bind does different things. It'll be when we give a value and we give a function mapping a value, it will give back the right value as applied, as defined by this function applied to this, the thing that's inside of this, monad. But in the meantime, it will have a side effect. It will print something out. Okay. Anyway, I'm not going to go into this more detail. I wanted to show you though completable futures. Okay. So completable futures are a monad that allows us to handle asynchronous computation. Okay. So the idea here is we're going to have computation going on where the pieces of that computation will finish at different times, okay? And it may be a while before something we request is done. And kind of the anti-pattern to avoid here, ladies and gentlemen, is calling off to something of just waiting a very long time, blocking until it's completed, as we say. That generally is not favorable. It may lead to a timeout or what have you. Generally speaking, ladies and gentlemen, the more scalable way to handle this is through what's called a callback. And what's the idea behind a callback? Can anyone say, roughly speaking?
It's a function that's executed after another separate.
Exactly. So ladies and gentlemen, once this thing we've requested is done, we'll get called back. Okay? We'll get told, hey, it's ready for you. It's kind of like ordering something via interlibrary loan at the library. You know, I go over, I may go to the desk and say, I'd like to order this item from interlibrary loan. And instead of just waiting at the desk for a long period of time, which would be uncomfortable and inconvenient, they tell me when it's in, and then I go pick it up, right? So, ladies and gentlemen, the idea with asynchronous computation is traditionally this is done with callbacks, but that often leads to scattered code because you got to code those callbacks somewhere else, and when the value is finally done, you got to enable the flow of control again or what have you. So instead, we're going to deal with completable futures, which are these kind of future values. We can handle them now if they're available, but if they're not yet available, we'll just queue up plans to handle them when they become available. When they become available, automatically the appropriate things will be performed. Okay? So the example I used last time was, suppose we want to wait for user input, and then perform a search using that input. And after all, it may be over a slow connection. It will take some time for that search to complete. And then we want to go through each of the URLs returned and do some sort of processing of the content of the URL, which will also take time, or the content of the page pointed to by the URL. Then we summarize the results. How do we do this? Well, it turns out in Java 8, we can do this through a series of operations. And this, again, is monadic. What's going on here is we have a value that's being computed, but the package around the values is keeping track of, amongst other things, whether or not this value is being computed and what to do next. When this value arrives, where do we go next? Where do we pass this value to next? Okay? So as we chunk along in computing this value, not only is it performing the actual operations if that value is there, but if the value is not there, this is key for understanding computable futures. If that value is not yet there, so we can't do these operations on it, what are we accumulating?
Plans?
Plans for what to do when that value becomes available. So that when it becomes available, we know exactly what to do and we'll go through those steps then. So it's not like your code freezes when the value is not available. After all, that would be this thing blocking, where it's just waiting, waiting until it's available. Instead, the code executes. It's accumulating up plans for what to do next. Does that make sense? Okay. So what you have is this whole series of operations, which are a little bit confusing to see at first. But check out the names. I don't want to expect you to know all the details of this, but I want to give you a sense of what's available in the basic functionality so that you can dive into it later as your professional life demands. Then compose, then apply, then accept. That's exactly what Eric's talking about there. These basically say, okay, if the value is available now, let's take then apply. Then apply takes in a function. Okay? What do you think happens if this value is currently available? If we have the value in hand, what do we do with this function?
Immediately apply.
We immediately apply it to the value. If the value is not available, we remember what needs to be applied. Right? And we'll be able to then apply it. Then accept. Here we have a consumer. Does anyone remember what a consumer is?
Takes in data and returns nothing.
Exactly. Takes in data, returns nothing. Maybe it prints it out. Maybe it sends some sort of message. Maybe it, over the wireless, maybe it stores it to a database. It consumes a value but doesn't produce a new value. Okay? And then there's a supply async, which provides a supplier. These are all Java 8 functions, ladies and gentlemen. Supplier, function, consumer, buy function. This is built atop Java 8 functions, like we talked about a few lectures ago. So supply async provides a supplier. What do you think that, well, as a supplier, what's his job in life? Yeah, it basically is going to be called with what as arguments? What do you think it's given as arguments? A supplier. Nothing. Zippo. And it's going to return back a value of type, well, in this case it's type T, right? So this could be a supplier of int, or it could be supplier of a string representing a web page, right? Or what have you. So this is going to be a source of data. So that can start our pipeline, for example. Then compose. What do you think this function does? Well, basically it allows us to have a next step in what we're going to do that's not merely a function, but involves some further processing. Okay. So here, ladies and gentlemen, we can define and hold these computations while performing other operations with assurance that they'll get done when needed. Okay? So here, remember our task. We want to wait for user input, perform a search, get the results of that search. Each of these is going to take some time to do. How long? We don't know. That's the whole point of asynchronous. We're not sure how long it's going to take. So we'll wait for it, and when it's available, we'll harvest the results of the search is available. We'll go through and get the URLs. For each of those URLs, ladies and gentlemen, we'll take them and perform an intensive analysis of the contents of that page and summarize the results. So how are we going to do this? Well, maybe it would be useful to see it this way. We're going to get out a sentiment score out of this thing, summarized across these pages. But how is that going to be computed? Well, first we're going to get this, and this returns a completable future. To be very clear, this get submitted search term returns immediately. It just returns a promise. A promise, ladies and gentlemen. A promise of what to do when it's available. Okay? Now, naturally, if it is available, it'll just go on immediately and apply these things. But here's a promise of this. Then we compose it with perform web search, and we'll get back another promise involving a URL. Okay? So here, that's the results of the web search. And then we're going to go get, really I should have an additional one here, which go fetches that page and then applies it to extract the links. And then from that we get a list of URLs out. And in parallel here, we're going to read the URL contents, okay? And then we're going to perform sentiment analysis, and then we're going to map the result to the result of this, which I think is going to be a certain type of value that's not guaranteed to be double to a double, and we're going to average them. Okay, so yeah, here we have a computable future of double, and then we're going to get it, blocking if necessary there, and then we're going to take the average. Okay, so here, ladies and gentlemen, we'll take the average and get a double out. Okay, so typically, ladies and gentlemen, what's available here will not be available yet. It's a promise for something that's not yet available. But to be very clear, this all executes here up to a certain point, okay, where we're actually getting the value. And we might, instead of insisting immediately this be evaluated, we might get a promise out here that's a promise for a double and simply deal with that later, okay? So here we're insisting that by the end of this we get it, but in general we might deal with a promise, a completable future of that. And when those things are available, they will get done, okay? So when this finally returns, it will go on and execute this. It will go on and execute this. It will go on and execute this. How does it know to do that? Because the monad, the completable future, has accumulated the information about what to do next, about the whole pipeline that's needed. Now you can imagine just as well writing your own monad, which would accumulate the whole sequence of how this value was derived, what was applied to it when, at what point it was added to this other value, what have you. That'll be another monad you could do with this information. This one accumulates it and applies it. Okay, so here's another example, right? We scrape a web page, and then we apply some harvesting to it, and then we apply some aggregation, then we insert it in the database, and these things will occur when they're good and ready. When they're good and ready, that information will be harvested, it will run through this, and in the final analysis, it'll insert it in the database. Right? Stick it into this database. Okay, so ladies and gentlemen, I want to thank you for your patience with my condition, patience with this material, and what's no doubt as yet a crude sort of approximation for what's needed for teaching it properly. There are some great references on this if you want to dive down that will provide additional understanding of monads and their role and how they can be used to simplify computations. Give some examples of cleaned up code where monads have been applied, etc. And I would enthusiastically suggest some of these. That's all for now. Thank you very much. And again, if anyone needs to talk with me, I could do it between now and 1 o'clock, although I'll have to prepare my 371 lecture sometime in there too. So thank you very much. Appreciate your accommodation, and we'll have to see what's going to go on for next week. I'm not sure quite yet. Okay?